Hi, so I've been asked many times to do this, and I finally got around to doing something about it, and that is to give some talks about some of the basic concepts of chemistry. Now, the first question you've really got to ask yourself is, what is chemistry? Well, chemistry is the study of matter and energy and the interactions of them, which incidentally is exactly the same description as the study of physics. And that's no real surprise, they're both two sides of the same coin. The physical sciences are what we like to describe as the hard sciences. And so they're very, very closely interrelated. Now, chemistry tends to study the interactions of electrons and matter at a slightly more gross level, whereas physics tends to have a look at the nucleus and the subatomic level. But it's only a distinction. Now, when you're going to study anything, or you're going to think about anything at all, you need two main things. The first thing you need is some organisation in which to study it. Some kind of like system, almost like a pigeonholing system, where you label up a lot of boxes, the letter arrives and you stick it in the right box. It helps you organise your thoughts and organise the way you think about these things, so you can form a structure of understanding that can help you work out what's actually going on. And the other is focus. You need to focus on what you're doing and try not to drift off too much, otherwise you get very confused. Now, having organisation and focus seems a very simple thing to say, and it is a simple thing to say, but it's stunningly difficult to do. It's much easier to lose your organisation and drift off your focus. If you find yourself doing that, what you need to do is pull yourself back on track in order to gain an understanding of what it is that you're trying to gain an understanding of. Now, these pigeonholes I mentioned aren't fixed. They're only useful ways of looking at something. So there is no right and wrong in anything. Very often you're told about a universal law, and that universal law is true for all time. Well, yeah, I guess so. But strictly speaking, it isn't. And when we find out it isn't, we go, oh, that one was wrong, but our new universal law is right for all time and all space. It's quite laughable, but there is nothing that is right or wrong in these terms. They're only pigeonholes that are useful. So when we talk about some of these ideas, what I'll be doing is presenting you with a sort of framework that is useful. So there's no point in writing back to me telling me that, hey, this is not true, this is like this, this and this. I'm highly likely that I know it. It's just that I'm trying to give people a framework in which to kind of get hold of some concepts of chemistry in a way that is useful. And these concepts that I'm going to be presenting to you are very useful concepts. They've been used for centuries to try and get hold of what's going on, and they're very good for making predictions and thinking about the way things are working. Later, we'll come to look at things slightly differently, but that will just be relabeling a pigeonhole set as opposed to trying to get hold of a whole range of concepts. So if I say something like, the electron is an infinitesimally small dot of matter that carries a negative charge, it's just a pigeonhole. We all know that an electron actually has very strange properties. Asking questions about those properties and what is the shape of the electron, where does it come from, all that sort of stuff is very interesting and all very good questions, but at this stage they're outside of the framework that we're talking about. So those kind of questions will in fact just help you lose focus. They're good questions to ask them at an appropriate time. At this time, what you're trying to do is get hold of basic concepts, and so to an extent, just accept the framework that I've given you, because it's a way of dealing with those concepts and describing those concepts to you. When it comes time to question them a little bit further, well, we'll question them a little bit further once you've got hold of the concepts and a framework in which to question them. If you question everything all of the time at every single stage, in fact you'll just utterly confuse yourself and lose track of absolutely everything. So bear in mind, it's important to have a framework that is useful. There's no question of the framework being right, it's only useful. And it's also important to maintain a focus on what it is that you're doing, as opposed to drifting off asking irrelevant questions, that is, questions not within the focus of what you're doing. Now, when it comes to chemistry, there are really, I think, two basic concepts that you need to have a fairly good grasp of. One of them is, what is the atom? And the other is, what is a bond? these two ideas of the atom and the bond are predominantly what govern all chemical interactions and pretty much what every chemist is actually looking at. So when you're looking at those two concepts, you're looking at chemistry. So what is an atom? Now, there are a lot of different ways of looking at the atom. Traditionally, and this really began in about the sort of 12th century, traditionally the atom is seen as a kind of a ball. On the centre of the ball is a nucleus, on the outside of the ball is the electron, seen as a small particle carrying a negative charge, travelling the surface of the ball. Now, that's not strictly true. And that's okay, that's not strictly true. But it's a good way of looking at what an atom is. An atom is the smallest particular part of matter that can't be subdivided any further. That's a Greek idea, incidentally. Once you get down to that smallest part of matter that you can't subdivide any further, you're at the atom stage. Now, of course, you can subdivide it. You can subdivide into the bits that the atom is made up of. But think of it like that at this stage, and that will help you greatly. Now, the atom being made of the nucleus in the centre, carrying a positive charge, and the electron on the outside of the surface whizzing around at Mach 10 carrying its negative charge, to give you an overall neutral atom. It's a useful concept. In the centre, there is really two bits. There's the proton and the neutron, and they make up the nucleus. The proton carries a positive charge, which is responsible for attracting the electron, and the neutron carries no charge whatsoever, but is responsible for the isotopes. So let's take hydrogen. Hydrogen is the simplest atom. It has a nucleus of only one proton. Because the proton's got a positive charge, it will attract a negative charged electron. Now, a handy way of looking at this is the electron travels with energy or speed. If you get a bucket full of water and you start whizzing it around, what you'll notice is that bucket will try to fly away from you. It's kind of a centrifugal force, it'll fly away. The more energy the electron has, the faster it spins. The faster it spins, the further away it gets. The slower it spins, the closer it will get to the nucleus. Now, the nucleus attracts a charge on that electron and pulling it to the centre. The spin has an opposite force pushing it away. So these electrons spin at a fixed distance, depending on the energy that they have, from the centre of the atom itself. Now, this net positive charge that the nucleus has can change. Hydrogen's one, obviously. What happens if you get two? Well, if you get two electrons attracted, and you get helium. And so on. As the number of protons increases, then the matter changes, and we progress along the periodic table. The periodic table is actually arranged in numbers of protons. So if you look at it and you begin your counting across your hydrogen, helium, lithium, boron, carbon, oxygen, nitrogen, fluorine, as you go along there, the protons are increasing in number. Now, as you increase the number of neutrons, you change the isotope. So hydrogen has one proton, deuterium, which is an isotope of hydrogen, has 2 neutrons, tritium has 3, and so on. Deuterium has 1 neutron, 1 proton, and so on. It just continues to grow as an isotope. Because the charge isn't changing, the electrons it attracts doesn't change, and so the element stays the same, but the isotope changes. So that's a very, very handy way of looking at what an atom actually is. Now, that movement of the electron is very significant because the electron is what's responsible for the bond. The chemical bond is the way in which charges on the surface of the atom are shared between atoms. Now, if there weren't any charges between atoms, everything would float off. We wouldn't have tabletops, we wouldn't have metals, it would all just dissipate, fall apart, and we're one big old grey sludge. But we do have these attractions, and there are different kinds of attractions. These attractions hold matter together. Now, there aren't that many different kinds of attractions. So let's have a little bit more of a think about this idea of the electron spinning around the nucleus. Now, if I take my bucket example again, and I'm whizzing my bucket around, I'll feel it tugging on the string the faster I whiz it. If I let go of that string a little bit, then it'll feed out gradually from one point to another point, depending on how fast I'm spinning it. Now electrons don't do that. Of their nature, what they will do is jump from point to point. So they'll spin around at the lower shell until they get enough energy to jump from the lower shell to a higher shell, just in the same way that your bucket will move out, but instead of moving out gradually, they jump. Now, as they jump from that energy shell, which is actually a predetermined distance, it's pretty much the same in every atom. As they jump in that shell, they'll do it discretely, not continuously. They won't move slowly out there, they'll literally jump out there. And as they spin in the higher shell, if they lose energy, they'll fall back down to the lower energy shell. Now, as they do that, that extra energy that they had, that they're now giving up, is then shot out of the electron, and we perceive it as things like X-rays and light. That's what light is. Light is the electron dropping from one energy shell down to a lower energy shell, and it gives out light, because that packet of energy has to be lost somehow. Because it's discrete, it's lost as a discrete particle, and we see it. We see it as light, or we pick it up as X-rays or radio waves. Now, this concept of energy shells is key, again, to bond formation. These energy shells can only get so full, and it's not unreasonable if you think about it. If you have something that's quite close, the amount of area you've got there is very, very small, so the number of electrons it can actually cope with until it's full is small. And the lowest energy shell can actually only take 2 electrons. The next energy shell out, because the area is bigger if you like, can take more electrons in there spinning around it, and so on and so on. Now, if it's quite close, it's held quite tightly. If it's very far out in something like lead, it's held quite loosely. So those outer electrons are held to the atom, but they're jolly easy to knock off. And of course, you find that some atoms will hold on to their electrons extremely strongly, and some atoms just let them go really rather easily. And this is an important thing to think about when we come on to bond structures. Now, bonds are all about the way in which electrons share each other and the way in which atoms join together to form molecules. One of the important things about bonds is that if the molecule is a lower energy state than the atoms that make it up, that bond will form. If not, obviously, it won't do it. Now, that makes sense. Things like to be in a lower energy state. Just ask yourself the question, would you rather stand up all day holding your arms in the air, or would you occasionally like to sit down? You like to sit down because you're in a lower energy state. It's much nicer and more relaxing to sit down. Same thing with atoms. They like to sit down. If they're in a system where there is a lower energy state available to them, they'll take that lower energy state. So if you put atoms together where the bond state is lower energy, the individual atom state, they'll form bonds and they'll form molecules. A molecule is where 2 or more atoms are joined together in a lower energy state. Now, luckily, there aren't actually that many bonds. Bonds are a way in which electrons are shared in order to form a lower energy state, and there's only really 5 or 6 of them. We'll consider 6. The 2 most important ones, the 2 strongest ones, the so-called Ionic and Covalent Bond, which we'll talk about in a minute. Then there's the metallic bond, and then there's 3 other weaker bonds that are still quite important because they govern the interactions of materials. And they are the Ligand Bond, the Dipole bond, and the so-called hydrogen bond. We used to call the hydrogen bond the Ligand Bond. A ligand is a person who hangs around in a group not doing very much. They just hang on because they get their self-importance from being a hanger-on in the group. And ligand bonds or hydrogen bonds are very similar. They on their own don't do very much, but they do have an effect, and they're important in things like solvents. So let's go back to this idea of a metallic bond, because I think it's probably the easiest one to start with. Most matter is subdivided into metals and non-metals. It's kind of almost an arbitrary subdivision, actually, because of course you get the semiconductors or semi-metals. Carbon, incidentally, in its graphitic form is a semi-metal. But this division of metals and non-metals divides up the periodic table. Metals have certain qualities that make them metals. They're conductive, they're malleable, they're shiny, that kind of thing. They're formable. And they sit in a kind of sea. So when you get a whole group of metal atoms together, then they're quite readily give up the electrons in their higher energy cells to form a sea of electrons around the bulk material. And that's the metallic bond. And it's responsible for an awful lot of the things like the ductility of metal, if you think about it. Now, this sharing of electrons in the metal bond is very similar to the covalent bond. If you bring two atoms together, the nucleuses will have a property of repelling each other, just like the south-south of a magnet. Two like poles of a magnet repel each other. So if I put two like poles of a magnet down on the bench and let them go, they'll force themselves apart. If I get the opposite pole and drop it in between, what will happen is that those two poles will move closer to each other, and that's exactly what happens in a covalent bond. The nucleuses with their positive charges are actually pulled closer together, and they share the electrons in a very similar way to the metal sea. And those electrons now, instead of spinning around the individual atoms, spin around the shared atoms, pulling them closer together, and they're in a lower energy state, and that sharing of electrons in that way is a covalent bond. Now, most carbon chemistry is governed by covalent bonding. They like to share their electrons. Now, ionic bonding is where a transfer of electrons takes place. You remember earlier I said that some atoms like to grab electrons very, very strongly, and some like to give them up because they don't have particularly good hold of them. That's exactly what this is all about. One atom will come across that loves to grab electrons, and it will do, it'll pull it away. Another one is quite happy to let it go, and it will do. So you get now an atom with either a net negative charge or a net positive charge. And because now you've got two opposite charged atoms, then they're now attracted to each other, and they hold themselves quite closely. Now, the interaction between them is not directional, it's universal, it happens all over, all around it. And it has an equal pull in every single direction. For a covalent bond, that's not true. Covalent bonds are directional. So as they're pulled together, there's a direction of attraction between them. What this means is that the ionic bonds have a tendency to form crystals. The bonding across the bulk of the material is actually quite brittle, whereas in covalent bonds, the bonding across the bulk of the material is actually much stronger. So ionic bonds, although they're stronger between the atoms, they're actually weaker in the bulk material, so you find them quite brittle, they fracture quite easily down planes of fracture, whereas covalent bonds, although they're slightly weaker bonds, actually hold the whole bulk material together much more strongly. And you can see this in things like table salt. Table salt is your classic simple mineral salt. It's sodium and chlorine. Chlorine's grabbed the electron, the sodium's given it up, they're attracted to each other, they're attracted universally, so they form a crystal structure. They have cleavage planes. When you look at the crystals of them, you can see a definite crystallinity. And they have the traditional classical characteristics of ionic bonded material, whereas a covalent bonded material is something like a polymer or a wax, where they're much more pliable, they're actually quite difficult to break the material at the bond level, and they pull much easier, they're quite flexible, they have the traditional classic covalent bond structure. So they have an effect on the bulk material because of the nature of the bond between them. Ionic and covalent bonds are really interatomic bonds. They result from the sharing of electrons between atoms. Now, electrons can also be shared between molecules, and the intermolecular bonds, which are the ones that we just talked about earlier. They are the hydrogen bond, the dipole bond, and the London bond. They arise because of the movement of electrons around molecules. Now, some atoms love to grab electrons. We've talked about that before, and that's a property called electronegativity. Now, if an atom likes to grab electrons strongly, then it sets up a dipole. A dipole is just something with two poles, so a magnet is a dipole, it has a north and a south. Now, if the particular atom grabs enough electrons in a permanent way, then it forms a permanent dipole with a positive and a negative charge, like a needle, if you like, with a positive and negative charge on each end. And that dipole obviously sets up an electrostatic force between any other dipole that it will come across. And hydrogen chloride is a fine example of this. Now, a particularly strong permanent dipole happens when you get two atoms together where one is strongly electronegative and one likes to give up his electrons quite easily. And water is a fine example of that. Oxygen, fluorine, nitrogen, those kind of atoms are very strongly electronegative. When co-joined with things like hydrogen, then those electronegative atoms will pull the electrons into their orbital and they will hold them there, forming a strong dipole. Now, strong dipole or hydrogen or ligand bonds, they're all the same thing, are responsible for an awful lot of the properties of things like water and ammonia, the high boiling point, the fact that it holds together as a liquid. Those sort of things are a direct result of the strong dipole attraction that water has. Now, this ligand bond, hydrogen bond formation, is really labelled up by itself because of its importance in things like solvents. Water is a brilliant solvent for an awful lot of classic mineral salts. It'll dissolve table salt. The reason for that is that, remember, an ionic bond is omnidirectional. It doesn't have a specific direction like a covalent bond. Its force is applied universally. If you get a strong dipole approaching it, then it will effectively neutralise the ionic bond between the two different atoms, and the whole thing will dissolve, because that now charged atom is surrounded by the hydrogen bond, which takes up the charge, and then because it's a dipole, the other end will take the negative charge, the positive charge and negative charge, and the classic mineral salt will dissolve in water courtesy of the hydrogen bond. If you get a particularly big molecule, something like DNA for instance, then those electrons aren't static, they're moving all of the time, and they set up temporary dipoles. Those temporary dipoles, which are actually slightly stronger than van der Waals forces, are what we call the London bond, and they're responsible for an awful lot of the bonding and holding together of proteins and DNA and large molecules. So those are the basic intermolecular bonds, as opposed to covalent bonds, which are the basic interatomic bonds. So we're looking at bonds in terms of electron sharing. Now, I said before they would give you pigeonholes and that we would develop those pigeonholes as we went along. So it's not strictly true that they're electron sharing. Actually, what they're sharing is electrostatic force. So the swapping over of an electron and ionic bond, what it actually does is create a positive and negative charge. So it's not strictly sharing an electron, it shares the electron but then sets up an electrostatic force, and that electrostatic force is what's responsible for the bond. We think of it in terms of electron sharing because it's a handy way of getting hold of the concept. Once you've got the idea of the electrons being shared, then we can move on to the idea that that sharing is in fact the setting up of an electrostatic force. That electrostatic force is what's responsible for the bonding between things. So the sharing of electrons leads to an electrostatic force. The electrostatic force is what the bond actually is, and obviously that's an energy that's required. The electrostatic force in ionic bond is obvious, it's a plus and a minus. The electrostatic force in a covalent bond is slightly less obvious because it's kind of much more of a sharing model. Same thing in the sea of electrons, but the fact that it's an electrostatic force is very easy to understand when you come to the intermolecular bonds, because the movement of the electrons, whether in a permanent state or a semi-permanent state or a fluctuating state, leads to permanent or fluctuating electrostatic forces which are responsible for the things like the London bond, the hydrogen bond and the dipole bond. They're in fact bonds based on electrostatic forces set up by these concepts of electrosharing that we've been talking about. So those bonds are really interactions of electrons. They're really the way that electrons are shared between atoms to form molecules. And as I say, there aren't that many ways of sharing electrons, and electrons are shared in relationship to the forces of attraction between the nuclei and the movement the electrons have in their energy shells. So that's all there is to it, really. So to recap briefly, we've talked about what it is you need to do when you're looking at something. That is, have a framework and keep your focus. We've looked at what is an atom, we've looked at electrons and energy shells for electrons, then we've looked at electron sharing and how that electron sharing is divided into the kinds of bonds and how those bonds roughly will start to have some effects that we can observe. Now those basic concepts are the concepts we're going to use when we start talking about chemical interactions. Anyway, I know this has got a bit long, but I do hope it was of interest to you, and thank you very much for watching.